video module consists of a video program presenting an overview of the topic and a manual containing much more detailed information as well as exercises. To master each topic, you must use the module's components together. View the video program, read the manual, and work the exercises. Mud logging is generally thought of as a relatively simple process. We sample the cuttings and gases carried to surface by drilling mud, and from these reconstruct conditions at depth. As with all practices related to exploration and production drilling, however, things are never as simple as they seem, and mud logging is no exception.
Welcome to our module on mud logging. Before we have a chance to examine any bottom hole cuttings brought to surface by the drilling mud, these materials will undergo a number of changes. Bottom hole cuttings will be mixed with uphole cavings, diluted by fluid incursions, and modified by declining temperature and pressure conditions. And of course, we have also to contend with other factors. Contaminants, like lost circulation material or diesel oil, may be circulating in the mud. Sampling procedures may vary, and the sensitivity of our analytical instruments may change. Each of these variables can affect our observations. In this module, we'll show you the routine of conventional mud logging at the well site and explain how we try to adjust for all of the variables so that we can evaluate downhole conditions. But first, let's look at how the mud logging service originated and has evolved.
Mud logging originated as a well site practice in 1939. Its objective was to sniff for hydrocarbon gases arriving at surface in drilling mud in order to evaluate oil and gas conditions at depth. The rationale was simple. If we measure an increase in hydrocarbon gases in the drilling mud at surface, then there should be a corresponding increase in the probability of a petroleum reservoir at depth. The analytical approach developed for the well site was just as simple. Gather the gases which escaped from the drilling mud as it left the discharge line and draw these gases off to a nearby detector where amounts of combustible gas could be determined. These measurements were then plotted according to the depth being drilled, as determined by a mechanical system which measured Bloch or Kelly movement. This made mud gas results comparable with wireline logs, and, it was hoped, identify possible productive zones missed by electric logs of that period. This initial measurement, total combustible gas, obtained from the hot wire detector, is still plotted on virtually all modern conventional mud logs and remains one of our basic parameters to determine the presence and magnitude of a gas show.
As gas analysis instruments became more automated and reliable during the 1940s and 50s, the mud logger had time to assume additional duties.
Describing cuttings, evaluating oil shows, and lagging samples. Many of those routine well site techniques we covered in the module on sample and core handling and analysis.
When total combustible gas plots and lithologic descriptions were combined with the rate at which the drill was making hole, that is, the rate of penetration, or ROP plot, the formation log was born. This log has become the essential summary record of conventional mud logging. Its preparation is a central theme of this module.
In the last 25 years, mud logging capabilities have expanded dramatically. There have been marked improvements in conventional mud logging analytical instruments and data handling techniques. Mud logging tools available today include such improved capabilities as chromatographic analysis of mud gas to measure concentrations of individual hydrocarbons, and computer calculation and drafting of mud log data. Formation log data can also be delivered by facsimile transmitters to home offices as part of daily reports. Other modern techniques have expanded conventional formation logging practices to provide a more thorough evaluation of conditions at depth. Analysis of fresh well cuttings for gas content and character is one example. Measurement of shale density is another.
In the case of cuttings analysis, we can make more accurate estimations of the nature of gas in a show or of possible reservoir conditions at depth because we are looking at the hydrocarbons still in the rock.
In the case of shale density, by plotting a density profile as the well is drilled, we can often recognize a change or break in the downhole profile and be alerted to the fact that the bit may be entering the transition zone of an overpressured interval.
As we will see, recognition of overpressure is very important when the modern practice of balanced drilling is used.
Still other tasks now performed by mud logging crews have branched far from formation logging. These are often referred to collectively as advanced mud logging. Their association with conventional mud logging in many situations is simply that all of the tasks are performed in the mud logging unit at the well site. Although we will not dwell on these in this module, let's look at a few examples. Advanced mud logging services include engineering functions, such as providing computer programs for maintaining balanced drilling or monitoring well kill activity. Safety functions, such as providing instruments for sensing dangerous gases or mud conditions. Or drilling functions, such as providing telemetry systems for monitoring rig operations on and off the rig floor, or providing downhole tools for making measurement while drilling.
Now let's concentrate on conventional mud logging with its formation log and see how we reconstruct the conditions at depth from cuttings and mud gases.
Conventional mud logging starts here. As the bit crushes the rock, cuttings and liberated fluids are picked up by the circulating mud to be borne up the well annulus toward the surface. And it ends here, with descriptive and analytical data summarized on a formation log. Getting from here to here is the task of the mud logging crew. Most modern formation logs consist of a rate of penetration curve, lithology and oil show plots, a total combustible gas curve, individual hydrocarbon gas plots, plus a descriptive track to provide room for written comments related to lithology, mud conditions, tests, or any information pertinent to interpretation of the formation log. Modern logs can also show both total content and individual components for cuttings gas. In addition, if such parameters as shale density or non-hydrocarbon gases are measured during mud logging routines, they also may be plotted in one of the columns of the modern formation log. From its overall appearance, you can see that the formation log is similar in many characteristics to wireline logs. Its heading, for example, provides the necessary detail for accurate location and well description. Its vertical scale, as another example, normally matches that of wireline logs run in the same well. This permits direct visual comparisons to be made between them. However, the formation log is also considerably different from the wireline log. For one thing, besides containing more curves and plots, it carries much descriptive detail. As you can see here, there is information on mud properties, operating conditions, bit changes, casing sets, hole deviation, and depth of hole each midnight. A completed mud log actually represents the total drilling life of the well, not just downhole runs made at short intervals while drilling was suspended and the drill pipe was out of the hole.
The formation log, unlike the wireline log, is a well's graphic diary or chronology prepared throughout the drilling life of that well. And because it is prepared as events occur each day, it can be used in two ways.
One, as an immediate reference to downhole conditions shortly after they are encountered by the bit, and two, as a historical record of the drilling activity of the well. Returning to conventional mud logging, We have indicated that a number of modifications occur to cuttings and fluids from the time that the bit crushes rock at bottom hole to the time that samples are available for evaluation at surface.
Let's look at the most common modifications, particularly those related to cuttings and mud gases, so that you are aware of them when working with a formation log.
As the bit grinds ahead, cuttings and entrapped gas, oil, and water are released. The gas which escapes from the crushed rock is called liberated gas. Liberated gas, and of course liquids as well, join any other gases recycling in the mud and move uphole with the cuttings. The cuttings, at the same time, will become mixed with any sediments recycling in the drilling mud. The amounts of recycled gas and rock particles will depend to a large degree on the use and effectiveness of desanders, desilters, and degassers in the mud system at surface. As this mixture of bottom hole and recycling material moves up the well annulus, it may be joined by produced gas seeping in from permeable formations and cavings sloughing from the borehole wall. The volume of these additions to the mud system will depend in part on the stability of the rock in any uncased section of the hole and the effectiveness of mud cake and mud overbalance to prevent influx of fluids. And it also is possible that this whole mixture can be churned up wherever the borehole is irregular, so that cuttings and gases from the mud above will be added to our sample interval. As this further modified mixture continues uphole, the hydrostatic or confining pressure of the circulating mud is reduced, and more liberated gas escapes from cuttings as all of the gases in the mixture expand.
The hydrostatic pressure drop, together with the temperature drop which occurs during uphole travel, also permits complex phase and solution changes to occur between gases and liquids in the mud, and between gases and liquids still in the pore spaces of the cuttings. All of these changes related to reduction in pressure and temperature continue on to surface and may even continue at surface, as we sometimes see in so-called bleeding cuttings.
So here's our mixture of cuttings, cavings, gases, contaminants, adjusting to surface conditions. This is what the mud logger has to work with as the returning mud flows into the possum belly through the gas trap and across the shale shaker.
To keep our approach systematic, we are first going to look at tracks and plots which are prepared mostly from the data reflecting rock being drilled. That is, the rate at which the bit penetrates the rock on bottom and the lithology and character of the cuttings produced. Later in Unit 2, we will study the data which come primarily from the gases and liquids recovered from the mud and cuttings.
Rate of penetration, or ROP, is developed from two inputs: a Kelly monitor, which measures the amount of hole drilled, and a clock system, which is keyed to on-bottom time. The most commonly used Kelly monitor is this sensor wheel. Typically, it is driven by the same cable that drives the driller's geolograph, measuring the Kelly's up and down movement. Since our Kelly monitor is tied into the same system as that activated by the driller while drilling on bottom, it is practical to measure Kelly movement related to drilling and, with the same equipment, ignore Kelly movement related to connections and trips. Consequently, this system also provides an accurate measurement of on-bottom time, which is essential for calculating the true rate of penetration.
While the bit is drilling ahead and the Kelly is moving down, each rotation of the depth wheel sends a signal to the mud logging unit. This in turn activates a counter which then records the new bottom hole depth or drill bit depth.
A simple mathematical calculation carried out at equal footage intervals or equal time periods yields an ROP value in minutes per foot or feet per hour. Or if the metric system is in use, ROP will be expressed in minutes per meter or meters per hour. In nearly all cases, ROP measurements are averaged over a drilling interval, 5 feet as shown here. In this example, we have plotted the ROP average as a bar graph. When ROP is plotted in time units, the increments, such as minutes per foot, decrease to the left. The inverse is true when distance units are used. Feet per hour values increase to the left. With these formats, an increase in penetration rate always shifts the plot to the left. This practice serves a specific purpose. It produces a left-hand formation log track, which is visually comparable to left-hand track wireline logs, measuring parameters related to rock drillability. The comparison between ROP plot and a spontaneous potential log curve shown here demonstrates the relationship. Both are responding to rock type of the wellbore.
And this brings us to the use of ROP data. When you stop to think of it, penetration rate is the first direct indication that we have of the conditions at the bottom of the hole. It is nearly instantaneous transmittal up the drill string of the bit's response to rock on bottom. It may proceed by an hour or two, information being carried to surface in the circulating mud.
A number of factors control penetration rate. Some are related to the drilling system. The condition of the bit is an example. Certainly, as a bit wears and becomes dull, it will make hole more slowly. Penetration rate will drop. Other factors are related to drilling operations. An increase in rotary speed will generally result in an increase in penetration rate. More energy is being applied by the bit in the same time interval. An increase in mud weight, in contrast, will reduce penetration rate. The added mud weight acts to hold down the rock below the bit face.
But at this point, we are most interested in what the penetration rate can tell us about the drillability and the pore pressure of the rock on bottom.
If drilling systems and operating conditions are relatively constant, we can then observe the effects of rock drillability and pore pressure. Here we see that as a bit passes from one lithology to another, the rate of penetration changes because different rock types have different drillabilities. Lithologies like anhydrite, limestone, and dolomite generally have poor drillability. Shale and siltstone, followed by sandstone, generally are more drillable. And unconsolidated sand, coal, and salt have high drillabilities. Here is pore pressure effect. You can see the change in rate of penetration as the bit moves from a normally compacted rock to an undercompacted rock of the same lithology. That is, into an overpressured zone. In this case, penetration rate increases. Overpressure, that is, an unusually high pore or formation pressure, will result in an increase in penetration rate for two principal reasons, if all other drilling factors remain the same. First, the rock is more drillable. The grains in the rock are being held apart by the high pore pressure, so that the drill is more effective in physically breaking the rock apart. Second, there is less differential between the pore pressure and the mud weight at the bit-rock interface. Therefore, mud hold-down pressure is less, and the drill will cut more effectively.
Drillers don't mind the increase in drilling rate as a result of very little mud overbalance. Taking full advantage of low interface pressure is in fact a principal objective of balanced drilling. Generally, the faster a rig can make hole, the better, as long as cost and other operating factors remain the same.
What may be a problem in this situation is the fact that overpressure is present. The situation may be developing where formation pressure will continue to increase abnormally and will exceed the counterbalancing weight of the drilling mud. This will permit formation fluids to enter the hole, further lighten the mud, and increase underbalance. This sets the stage for a strong well kick, or even a blowout.
One important thing to remember from all of this is that we may be able to recognize transition from normal formation pressure to overpressure by an increase in the penetration rate. At the drill site, this and the maintenance of correct mud overbalance is a critical task of mud logging.
Experience shows us that when ROP data are systematically plotted, a number of features generally can be identified and projected to rock drillability and pore pressure conditions at depth. This ROP plot generalizes penetration rate in a thick, shale-dominated interval and shows ROP features which reflect different bottom hole conditions. First, you will note that there is a general trend from the top to near the bottom, indicating that penetration rate generally decreases with depth. This is known as the compaction trend. This trend should be recognizable in well segments drilled with the same diameter bits if good balanced drilling practices and consistent operating procedures are being followed. The compaction trend indicates increasing lithification with increasing overburden pressure. Deviation from this anticipated trend may indicate undercompaction and overpressure. That condition is represented by the increase in penetration rate or drill-off trend in the shale section near the base of the curve. This is the curve trend you should expect in the transition zone above an overpressured interval. Next, you can see that for each bit run within the normally compacted section, there is a fairly consistent decline in penetration rate with depth. In this case, it is called the shale baseline. If the section drilled were in a carbonate section, a dolomite or limestone baseline could be established. The baseline reflects normal penetration rate for that bit with slight influence of wear, and it serves as a basis for recognizing breaks, typically due to changes in rock type. Drilling breaks and reverse drilling breaks, as highlighted here, are sharp increases and decreases in ROP, which occur when the bit penetrates rocks with different drillabilities. Breaks may be due to a change in lithology, as we have seen, or a change in porosity.
Drilling breaks due to porosity changes may be a good indication of a reservoir lithology. However, drilling breaks can also result from crossing sharply into an overpressured zone, as when drilling through a fault.
Now you can see that by using ROP data alone, it is often possible to gain very early insight into changes in rock type and formation pressure at the bottom of the hole. Let's move to the next track in most formation logs, lithology. When combined with ROP, the lithology track should provide further insight to bottom hole conditions.
Procedures for collecting samples and describing cuttings were presented in Module GL303. They serve equally well for the work of the well site geologist or the mudlogger. Cuttings lithology is generally presented in percentages for each sampled interval. As shown here, lithology is categorized in 10% increments and plotted horizontally to equal 100%. Because the sample interval in this example was 10 feet, each lithology plot covers 10 feet of drill depth. Order of presentation in the lithology track is most commonly coarse to fine, right to left. This places sandstone on the right of the track, grading left through siltstone and shale to limestone, dolomite, chert, and anhydrite. Remember, this closely parallels the normal decrease expected in rock drillability. Therefore, changes in the lithology plot should reflect or generally agree with breaks and changes in the ROP curve, if conditions are normal on bottom.
I'd like to point out here that the lithology plot will vary widely depending on how it is formatted and prepared.
As we show here, it may be simply an estimation of rock type percentages, in which samples are screened to remove large cavings and then described as is. Preparation of this basic lithologic percentage log is required by some operators. The lithology track may show instead cuttings as they are interpreted to have left bottom. This is called a corrected cuttings log and reflects the interpreter's skills and familiarity with the geology of the area. In some cases, a second lithology track is added to the formation log in which lithology is interpreted based on other available information such as ROP. This is known as an interpreted true lithology log. Regardless of which lithology log is prepared, abbreviated lithologic descriptions are included in the far right-hand track on the formation log.
You can see that the sequence of lithology plots just outlined became more subjective with each step away from the cuttings as they arrived at surface. You will want to remember this when using formation logs in conjunction with wireline logs.
While we're in the cuttings handling area, let's also look at shale density. We've talked about how overpressure will hold grains apart, particularly in shale, and make rock more drillable. Overpressure in effect leads to a lower rock bulk density.
A simple method used during mudlogging to measure rock density or recognize changes in density gradient is by using this graduated column in which the fluid gets denser from top to bottom. As you can see here, beads of different density settle to different density levels in this fluid. A shale fragment placed in the column also settles until it reaches density equilibrium with the fluid in the column. Using the scale determined from beads of known density, it is practical to determine the cuttings density. This we plot on the formation log at the sample depth. Under a normal compaction scheme, we expect shale density measurements to increase progressively with depth. When a shift or reversal from the normal gradient occurs, we may be seeing the transition from a normally compacted to an undercompacted or overpressured interval.
So just as we may be able to recognize the transition into an overpressured interval by an increase in the rate of penetration, we may be able to recognize or confirm the same transition zone by a break in the shale density gradient.
A transition zone can also be indicated by an increase in cutting size and volume, and in their appearance. These also are due to improved drillability associated with overpressure.
As with all geologic interpretations, the more confirmation you can get on a change in pattern, the stronger the indication that an anomalous condition is developing. This is a good place for a break. Take a few minutes to review the first 3 sections of the manual and complete the exercises. If you're not familiar with hydrocarbon gases, you should review that in section 4 of the manual before viewing the next video unit, where we'll examine these gases as they are recovered from the returning mud. In Unit 2, we'll look at the sampling and analysis of hydrocarbon gases and liquids which are brought to surface by the mud system. We also see how this information is handled on the formation log and what it can tell us about downhole conditions.
The gases analyzed during mud logging are those extracted from the returning mud by a gas trap such as this, or those released from fresh cuttings by the grinding action in a blender jar. The liquids generally examined are those in the cuttings from oil show intervals.
First, let's consider the gases. In the case of mud gases, the gas trap may be collecting liberated gases, recirculated gases, and produced gases, as we discussed in Unit 1. However, if drilling is proceeding ahead steadily and with consistent mud overbalance, then most of the mud gas which is extracted at the gas trap should be liberated gas. In the case of cuttings gas, we are generally analyzing that fraction of formation gas which has not escaped from the cuttings to the mud system during drilling and uphole travel.
Let's quickly follow a mud gas sample through the analytical cycle from the gas trap until it yields data in the mud logging unit. While you do that, I'll take a cuttings sample and begin the analysis. Cuttings gas analysis should be run as quickly as possible after the samples arrive at the surface.
Our gas analysis program is interested principally in those hydrocarbons which are gases at atmospheric temperatures and pressures: methane, ethane, propane, and the butanes. During mud gas sampling, a stream of returning drilling mud flows steadily through the gas trap. Inside the gas trap, typically mud is agitated. Gases in the mud escape and rise into the headspace in the top of the trap, where they mix with air entering the trap, and then are drawn off by a vacuum system. The extracted gas and air mixture then travels from the gas trap through tubing to the mud logging unit, and in the process is dried and filtered. Once ready for analysis, the gas is metered at a steady flow rate into the analytical system. A portion of the gas sample is split off to pass continuously through the total combustible gas detector, generally referred to as the hot wire detector. This detector produces a continuous reading, generally on a meter dial and a strip chart. This reading is a measure of all combustible gases in the sample.
The total combustible gas concentration will probably be reported in percent equivalent methane in air, or percent EMA.
What this means is that 1. A known concentration of methane in air has been used to calibrate the detector, let's say 1% methane and 99% air. 2. The concentration of mud gas that was detected has been equated to that calibration response. A calibration gas must be used as a reference value because a typical mud gas is a mixture of many of the combustible gases. The total gas detector combines their total response or sums their effects.
So to compare results over time and between wells, we must make all measurements relative to a known standard. Another portion of the mud gas sample is passed into a continuous flow loop. A batch sample is taken every few minutes for identification of individual gas components, which makes up the total gas reading.
This hydrocarbon compound analyzer uses gas chromatographic analysis, which typically takes 3 or 4 minutes to separate the compound types and measure their concentrations. Therefore, its output is cyclic rather than continuous. And the output for each cycle gives one reading for the concentration of each gas type. In other words, we can see the relative concentrations of methane, ethane, propane, and the 2 butanes present in each batch sample. But remember, these are only intermittent values. Cuttings gas analysis uses the same gas chromatographic system as that used to separate and measure mud gas compounds. The principal difference is that the Cuttings gas sample is drawn from the top of the blender jar instead of a flow loop. The output for each compound concentration in the mud gas or Cuttings gas can be expressed in percent equivalent methane in air or in parts per million, depending on what system or standard is being used.
It is at this point that the mud gas data becomes available for use in the formation log.
We went through the analytical steps rather quickly, but you can pick up the details from the manual. In addition, you should read to see how the 4 principal gas detector systems work and why we use different ones for different analyses.
To use mud gas information, we must decide what values are going to be transferred to the formation log.
There are far too many data points here in the total combustible gas curve to be plotted on a formation log.
We must use averages, trends, or extremes, which indicate something about drilling or downhole conditions.
You recall from Unit 1 that when rate of penetration data were plotted for a well, a number of features could be recognized and downhole conditions interpreted. The same is true for total combustible gas data. By recognizing distinctive features which are due to normal operating conditions, it becomes practical to recognize anomalous conditions and make some inferences about downhole conditions. True zero gas. From a strictly operational point of view, we need to know what gas reading is produced when the gas trap is inactive and only air is circulating through the mud gas collector system. We can think of this as the sampling system's baseline. Circulating background gas. Next, we need to know the level of gas recorded when no drilling is taking place and only mud is circulating through the gas trap. We can think of this as the mud baseline. Drilling background gas. Then, of course, we need to know what gas reading is normal when the rig is drilling routinely ahead. In other words, what addition of liberated gas is normal during balanced drilling for the interval being penetrated. Now let's look at some events. Connection gas. This event, or peak, in the total combustible gas trace represents the arrival of gas at surface, which accumulated in non-circulating mud near bottom hole, as a connection was made. Connection gas coming from bottom hole should pass up the annulus and arrive at the gas trap one lag interval after a connection is made and mud circulation resumes. Trip gas or any downtime gas. Such a peak indicates the arrival at surface of gas which accumulated in non-circulating mud during the time drill pipe was being pulled or run in, or while drilling ceased for such a purpose as running a directional survey. And like connection gas, trip gas should arrive about one lag interval after drilling resumes. Let me point out here one important condition involved in trip gas and connection gas. These gases can represent underbalancing events. As the pipe is being pulled off bottom, it has a swabbing effect on the open wellbore and a lightening effect on the mud. As we'll see later, this gas arriving at surface after drilling resumes can tell us something about changes in formation pressure.
But let's concentrate on the total gas curve characteristics for now. A variety of other events can produce peaks in mud gas measurements.
The principal one is lag gas. It will show up on the total combustible gas detector whenever carbide or hydrocarbons, like gasoline, are introduced into the mud system. This leaves us with the unexpected gas peaks, the shows, the original reason that mud logging developed as a service. These will represent some new conditions at depth, which cause more gas than normal to be in the mud system as drilling proceeds.
Now that we can recognize some of the features of a total combustible gas plot, and we have seen how data for individual hydrocarbon compounds can be reported, here's how you can expect to see this information incorporated into a formation log.
We have shown that 1 or 2 gas tracks are generally incorporated in a formation log to the right of the lithology track. In gas tracks, increases plot to the right, opposite the ROP track. This convention gives mirror images between ROP and total combustible gas plots if similar features are being measured. For example, an increase in penetration rate might indicate an increase in porosity, just as an increase in mud gas might reflect the same increase in porosity. For total combustible gas readings, an average is generally determined for each of the smallest intervals carried on the formation log. In our formation log, this interval is 5 feet. This average generally is plotted in the same visual manner as ROP averages, in this case, a bar graph. When we are drilling ahead normally, we can use the total mud gas plot of averages to determine drilling background gas. If we are analyzing total cuttings gas, we can generally plot its values on the same track as total mud gas. Where we are running cuttings analysis at predetermined intervals only, say every 30 feet as shown here, then we may plot values for individual analyses.
One of the interpretive uses of the total mud gas, total cuttings gas dual plot is to evaluate differences between them.
If both analyses are from a show interval, a relatively low content of cuttings gas compared to mud gas is often equated to favorable reservoir conditions at depth. The cuttings are assumed to have high permeability and to have given up their in-place gas to the mud system. Where individual hydrocarbon gas concentrations are determined in mud gas, total concentrations of each compound can be plotted, as we have shown here. Relative percentages of each gas within the total, as shown here, is an alternate plotting method. Relative percentage plots give a good visual representation of the gas composition, whether dry, mostly methane, or wet, abundant in the heavier gas compounds. These relationships are sometimes interpreted as indicating that gas, or oil, is most apt to be the type of hydrocarbons in place at sample depth. On the total combustible gas track, events like connection gas and trip gas, which originate while no hole is being made, are plotted as single lines on the formation log and at the well depth where the bit was off bottom. 2 features are important here, particularly for connection gas. 1, we use the maximum reading recorded, not the average of the event. 2, most mud loggers subtract drilling background or other gases present from the maximum connection gas reading that was recorded. By removing these effects, we can compare one connection gas value directly to others, uphole and downhole.
And being able to compare connection gases is important. You will recall that connection gas represents an underbalancing event due to the bit and drill pipe being lifted. If we see that successive downhole connection gas readings are getting larger and larger, then we must assume that mud overbalance is declining. One cause of this is increasing formation pressure. We should recognize that a progressive increase in connection gas can mean we are drilling into an overpressured interval.
Lag gas typically is plotted in the same manner as connection gas, the high reading above the background for the event. If we use the same amount of calcium carbide each time the well is lagged, changes in response can indicate a change has occurred somewhere in the gas sampling and detecting system. And other responses, gas shows for example, may need adjustment accordingly if they are to be compared.
When the total combustible gas readings increase markedly above the drilling gas background level, let's say the gas doubles, then a gas show is occurring.
In this situation, the driller may pull off bottom and circulate up samples. particularly if a drilling break occurred prior to the arrival of the gas. This mud circulation period will carry the cuttings from downhole to surface for evaluation and analysis. As part of the sample examination process, a thorough inspection for liquids, that is, an oil show, will be carried out. Interpreting a gas show is not a straightforward evaluation of the increase of total combustible gas measurements over background. A number of factors may be affecting the quantity of total combustible gas measured during a show which we have been able to ignore during routine drilling. Let's assume that penetration rate increased prior to a gas show being recorded at surface. A part or all of the increase in total combustible gas may be due to more rock being crushed and more gas being liberated. This will all return to the surface in the same volume of mud. In this case, total gas increase over established drilling background level may have little significance. If mud circulation rate has been recently increased, the opposite effect may occur. The apparent magnitude of a show can be diminished by mixing the liberated gas in a greater volume of mud. It is also possible that our show is out of place or smeared out. Drilling mud can penetrate ahead of the bit in a very permeable show zone and flush gas and oil from in front of the bit. These hydrocarbons may not enter the mud system until the bit has passed by and formation pressure has moved them back to the wellbore. And if overbalance is very high, the hydrocarbons may not show up in the mud system at all.
These are not the only factors which can modify responses in a show interval. And if you want to compare one show to another, the mudlogger must consider even more factors. These and the procedures for normalizing data are in the manual. Now let's see how a show is annotated on a formation log.
The depth interval across which a gas or oil show occurs is blocked out in the show column. The high reading for total combustible gas can be recorded next to the curve along with the averages near the show interval. And let's not forget that a show may be recognized visually, an oil show, as well as by gas analysis as shown here. Each show is numbered sequentially downhole as it is encountered. Then it is rated. The sequential number serves to identify the show and the show report prepared for it. The rating is the mudlogger's estimation of the quality of the show. In the situation seen on this log, the show was of oil, weak, and given a numerical rating of 5. That is probably non-productive.
Let's take a minute and look at the show report. Preparing this report exemplifies one of the routine tasks performed during conventional mudlogging. It is a written evaluation of the zone of interest which accompanies the formation log.
If oil is present, its fluorescence, cut, and character are recorded, together with the apparent porosity and permeability of the cuttings in which the show is found.
If gas is present, its magnitude and character are described. In this case, it is essential to qualify the magnitude of the show relative to the background gas level and many other factors we just covered.
Our formation log is fairly complete with the addition of show data. The remainder of the details to be included can be any information which adds to the understanding of the formation log plots.
You can see we have added mud details like temperature and density in and out, plus pump pressure and flow rate. We have drilling details like rotary speed, weight on bit, and condition of bit. We have downhole information like coring interval, drill stem test interval, and logging runs. And we have descriptive details like visual porosity and permeability.
This brings us to the end of our discussion of conventional mudlogging. You should complete the manual and work the exercises. The latter part of the manual discusses advanced mudlogging. We're going to leave you on your own for that.
Good luck.
This program has been sponsored in part by the following companies: Agip, Aramco, Chevron Corporation, Mobil Oil Corporation, OxyCity Service Oil and Gas Corporation, Petro-Canada Incorporated, Phillips Petroleum Company, Schlumberger Limited, the Shell Companies, Texaco Incorporated.